well, the whole point is simple, is that on top of having static information, what about if we can achieve some understanding of the flexibility of the macromolecule from the electron microscopy images? In principle, this is possible because electron microscopy images individual macromolecules. I am referring to the field of single particle analysis, to the field in which you have purified proteins. There is another very important application that is tomography that we also do, but I am not getting into that right now. So when you are imaging purified macromolecules, you are imaging each of these complexes. So you are not mixing the signal from one complex to another complex, mixing meaning that you may be doing an averaging or anything like that. So since you are seeing each of them individually, well, it is conceivable that you could study the information, the structural information of this macromolecule differentially from this one, from this one, from this one, from this one. And if you have a flexible macromolecule, this would be the way to sample conformational space. The reality is a little bit more complex than that, and we have things called air-water interface that are actually these interfaces between the ice and the vacuum or whatever you have put there. And these interfaces are really very complicated to understand what happened at these interfaces, but they may induce preferred orientation, they may induce denaturation of proteins. All means that the access to conformational space has some caveats. I mean, that is very good, and everything I'm going to be telling you always start from the notion of understanding which are the limits of what you are doing. So that from the images we could get different structural state. That is something that we knew from a long time, from the historic time almost, and this is one of the first times that we did it, doing simple image processing, and then with these images making classification and making reconstruction of a ribosome. We are talking of the 80s. And then the whole thing really changed when we introduced the maximum likelihood approach in cryo-electron microscopy that have been so successful in crystallography. The problem is different, it's not the phase problem, but we introduce it for the sake of understanding the a posteriori assignment of geometry to the particles, to the macromolecule. They are in principle free to move in the water, in the buffer, so you don't know in principle in which orientation they are. So you have to find that orientation, and also if we are talking that there is a flexibility, we want it to sort by that flexibility. However, when we first developed this method, which are being used right now and are responsible for most of the map that you can imagine in cryo-EM, in different incarnation in Relion, in CryoSpark, at that time, we knew that we were having a very big constraint. We were saying, listen, the projection, the images are coming from a very a small collection of very well-defined states, K states. And K was a parameter in the algorithm. So you don't know anything about your protein. And, however, you have to tell me how many stable states your protein has. Okay. There was, of course, a problem doing that. But at that time, we didn't know how to do anything better. So, and this has proved very successful, really. In many cases, you have clear, stable states, and this approach will actually get them. However, you have to guess the number of classes, and we expected that this would be complicated. In fact, I'm going to use this data set for several things in the talk. It's a data set produced by José-Maria at the beginning of the pandemic that we have used for many things. I'm going to present it just what happens when you start analyzing that data set and other data set with the programs that we developed with Relion, with CryoSpark, based in ML. The point is that since you have to guess the number of classes, the typical workflow is normally complicated hierarchical workflow in which you are guessing the number of classes, trying to get those that are more clear and discarding some and things like that. Well, we acknowledging that this works very well in many cases. At the same time, if you have a situation in which you have a continuous flexibility, when you don't have a few number of very stable states, this is going to give you problems. It's going to give you problems because algorithmically, we are not modeling the reality in a right manner. And what we have been trying is to get rid of that. And really, when I say we have to say, certainly my lab, but we are not the single people in the world. So the situation in cryo-electron microscopy has changed a lot in recent years, in the last 2 or 3 years. And now the topic of analyzing continuous flexibility is one of the big topics in the area of single particle analysis. And I want to pay respect to the different methods that work in the area. I'm going, of course, to concentrate into our own ways. Continuous flexibility. Well, I'm not really happy with having classes and, well, yes, but we would like to understand a little bit about rare states. We would like to understand about transitional states. I mean, what is happening for A to go to B and things like that. Eventually, which we are perhaps not now, we would like to attach probabilities and to get into a more dynamical landscape. So our aim here is to address the continuous flexibility approach, not to impose discrete classes. We aim at subtle change that may be masked by classification, simplifying the analysis process and minimizing decision and increasing algorithmic reliability. This is important because I say if you have a case in which you have flexibility and you insist in going by discrete classification, you would have instability because your modeling of the reality is not correct. The optimization would do the best and will depend on many things, and the result will not be. Okay, we will present you this conformational landscape, and then I will introduce something interesting. Is once we are able to know each image, how it has been, which is the difference of that of the macromolecule that gave rise to that particular image, we can derive new reconstruction algorithms that take into account the fact that not all projections are coming from the same macromolecule. And you will see that this immediately gets you into the capability to have higher resolution in those moving areas that normally come blurred in a cryo map. So I'm going to present you what we have done in the study of conformational state. The first approach we did that was the principal component analysis, linear approach. We used this data set of Jason McClellan, and we got the 3D principal component analysis out of the 2D images. So it's slightly more complex than having 3D maps and getting a PCI of these 3D maps, having images and getting a PCI of the images. What I'm saying is to get a PCA of the maps that you do not have from the images that you do have. So it's a trick here. However, and this is what now is commercialized in CryoSpark with the name of 3DVA. Okay, 3DVA is PCA This we published at the very beginning of the pandemic, and you see that these simple approaches, clinical component analysis, really didn't give us a very detailed understanding of. It was telling us that really there was much more than the closed and open states and things like that, but at the same time, there were not very clear trends. With that, we were able to follow transition in the RBD and MTD, that were important at the time, but 3 years ago. But clearly the methods were not powerful enough. And for that, we went into other approaches. I'm going to talk about two approaches. One, the formation field approximation and the density-based approximation. Which is the difference? The difference is in the formation field approximation. I'm going to start from this following modeling. My reality is that I have a macromolecule that has some flexibility. And I can characterize that flexibility by certain parameters. And I can attach to each image I am recording, that is coming from a different conformation of the macromolecule, I can attach the flexibility parameters to that. I can estimate and attach the conformation parameters to that particular image. So to my 500,000 particles, I will make 500,000 estimation of parameters, and I will, with all the errors of the world, of course, be able to tell you which is the deformation that happened to the average structure to produce that particular cryo-EM to the image. So it's a deformation field. Why then? And you will see at the end that this is especially important because with this deformation field, we have been able to do a reconstruction algorithm that takes into account the deformation field and deforms each of the images and is able to increase the resolution, the local resolution in moving blurred areas. However, I was from the beginning telling you to understand the limit of what you do. If besides flexibility, you have an issue of compositional heterogeneity, which is to say, your macromolecule doesn't have exactly the same composition. It is made of 23 chains, and it just happened that in your sample, not 100% have of the specimen have this chain. So some proteins are missing in some of the projections. Okay, I cannot model that as a flexible field. So if I have that situation, could happen also, I have to do something else. And this something else is the density-based approximation. Okay, I start with the deformation field base. Is to think that you have your specimen, your naive representation of the specimen is the Durothel, and then what you have really is instances of some deformed Durothel. That because your specimen is moving with respect to an average canonical reconstruction. The techniques is, our techniques is technique 3D, that I certainly want to talk about, to refer to normal mode analysis, to 3D flex. You probably know also, and you have probably heard of here, with Slavica Jonic working a lot in this area of flexibility also with the normal mode analysis and with now with some molecular dynamics information. And 3D Flex is coming from CryoSpark, and it was published perhaps a couple of months ago. And it is completely different in how things are done, but conceptually very similar to what I'm going to present you today. So I am telling you that in our case, the modeling is that you have a certain conformation, that is your average conformation, and you are going to deform that conformation with a flexibility field. And that flexibility field, in our case, what we are going to do is to express it as a linear combination of a certain base, the mixed 3D, that previously we had shown that had a number of properties that were interested from the point of view of getting rid of local minima and things like that. So the deformation field is GL and is going to be coded as coefficient of a certain base. I'm not going to get into many details. This is the shape of the base. This is a very mathematical thing. At the end of the day, we have an average reconstruction. We have the individual images. And what we try to do is the average reconstruction is deformed with the deformation field. And then we do a computer simulated projection of the deformed average image. Of course, in that projection, we do the CTF and we put everything that has to be put to make this computer simulated image closer to the experimental image. And then we just check how close we are from this computer simulated image from the test, from the experimental image. If this deformation field is not properly computed, well, the difference between this projection image and this experimental image is going to be very large. So we try to minimize this difference by changing GL. And we can do that in many ways. We do this at the beginning with power optimization. Now we don't do it in that way. We just do by a neural network, and we take the cryo-EM image, a classical encoder-decoder approach. With the encoder, we get a certain latent space that in principle is a space in which you don't know which variables are there, but are capturing the elements of variability of your image. Okay, we do know what is here because the decoder is not trained. The decoder is actually getting this element and multiplying them by the 3D basis and forming the projection in this way. If this latent element, if the elements of the latent space are not the mixed 3D coefficient, there is going to be a very large loss between. We are not going to be able to generate computer simulated images that are similar to the experimental images. So this is the way to force that this latent layer really computes 3D, the coefficient of the Ternix 3D base. We say 3D, Ternix 3D is a mixture of Ternix polynomials and spherical harmonics. So the thing is working very nice, and really what you have here, that really the pointer doesn't work so well, but what you have here is actually a reduced representation, a two-dimensional representation of the variability that we are finding. Each of the points here is an image, okay? So you have 500,000 images, you have here 500,000 points. And what we are projecting here is the vector of coefficients of the 3D polynomial. Essentially, we are trying to represent the variability that you have in your project, in your data set. And each of these points is then the average image plus a certain deformation field. Okay, what each of these points is telling you, really, well, is very simple to compute, and you see that you can explore this cloud and see which are the deformation that can be found there. Simple to do and very intuitive to understand. This is exactly the same to say that you can go over the cloud and you can really get the information over there. This is a case in which we have used that in practice. We were to understand the flexibility of a growth factor HER2 upon binding of one of the therapeutic antibodies, trastuzumab. What does it happen? I mean, is there any change induced by the antibody? Well, it's a therapeutic antibody, is doing something. So which is the change? Well, it was complex because really there were no clear classes. So we had, when we did this flexibility analysis, we found a quite continuous case that really we were just exploring this landscape of flexibility, and we found that really there was sort of a gradient between a compact and an extended conformation that probably would have been very difficult to get by discrete approximation because there are not discrete classes here. And then when we actually analyzed these different classes, or this different snapshot of in conformational space, we understood clearly this is the compact HER2, this is the this is the extended, the normal HER2, and this is the compact form of HER2. And very simple, the interaction that had to happen, for instance, with HER3, and here we have the dimerization arm of HER3, how it gets into the dimerization pocket of HER2 nicely in the extended conformation. Okay, this cannot happen in the compact conformation. So probably trastuzumab has many ways to act, but one of them is by acting in a very allosteric manner, far away from where it binds, making the dimerization reach of HER2 to be much less accessible, and therefore to make much more difficult the formation of heterodimers. One of the therapeutic actions of this thing that we have been able to get through this continuous flexibility analysis. Still, this approach cannot work for all, especially if you have composition and heterogeneity. This cannot work by first principle. Which other things could work? Well, what about if we consider the images and we do a per pixel, per voxel approach without any flexibility model behind or anything like that? Maybe thinking, why is not starting by doing that? And he's going through the flexibility. Yes, because with the flexibility, I am putting more mathematics in the whole thing. But I am able to take this mathematics into the reconstruction and get an enlarged reconstruction. With the density-based approximation, yet we don't know how to do it. Okay, the first approach there, I have to acknowledge it, is Cryo-Dragon, Ellen Zong, MIT, now Princeton, Gaussian mixture model, Steve Lutke, and we are there with Hetzira, which is, since it is relatively, well, it's new, it's yet unpublished, is, we have learned from the other, is sort of complicated. I'm not going to go into the detail, but there are a number of nice things, is that we are working in real space. And what that means? It means that you can put masks and that you can focus your flexibility analysis into areas of your specimen. In other cases, it's more difficult. I mean, Cryo-Dragon works in Fourier space. It's more difficult for you. You want to put a mask in Fourier space, fine. But normally, where you want to put the mask is in real space. So just to give you an idea of how it is working, it's a collaboration with Sir and Subramanian analyzing a number of strains of SARS-CoV-2. And here what you have is probably 1 million images, 1 million points. And you see in conformational space what happened with BA2 and what happened with one of the very early viruses. And certainly the pattern of flexibility is completely different between these two variants. We can zoom into one of them, and zooming, you get maps like that, that immediately are telling you, okay, all these sometimes complicated classification or close, up, locked. Well, they just come as a continuum of cases with valleys and with hills. So you can really go over the main hill and also understand the transition state in between. So really, this is still we are working on, so it's all to come, but is telling you the capability of the approach with a very challenging specimen. This is the case of BA2, in which really the flexibility is much more confused. There are much less defined hills in that conformational space. Okay, now something very direct is everything I have been telling you is about the capability to explore conformation, flexibility, and all that. You may be thinking, okay, I am happy to get that, but at the end of the day, I want my map to be better. Is that helping me? Well, this is going to help you completely. Why? Because, as I have told you already, the problem that you get a blur reconstruction in a part of the map that is the specimen is moving is because the 3D reconstruction algorithm normally take as principle that all images are coming from the same specimen. And if they are not coming from the same specimen, well, there is a blurring. However, so you are violating the principle of 3D reconstruction if you want to get a 3D reconstruction out of a set of images which are not exactly from the same specimen. What about if we reduce this reconstruction artifact by changing the reconstruction algorithm and say, listen, the reconstruction algorithm now is going to be much clever. It's going to know that each of the images is not coming from the same specimen. Each of the images is coming from this flexible analysis that has been done before with this Fermi coefficient. So the reconstruction image, the reconstruction algorithm is aware of the flexibility. If it's not aware, when you get this nice thing that you don't like at all in the reconstruction. And if you are aware of the fact, you may get better reconstruction. Well, the way to do that could be complicated, but really with the GPUs and all that, we can do in a simple manner, which is modifying an existing algorithm that is called arithmetic reconstruction technique. Those of you in tomography probably are more used to another variant that is called SIRT, simultaneous iterative reconstruction technique. Okay, there were many fights between SIRT and ART, but essentially they are similar. And they are iterative, and here this is the normal ART, and the single difference with the ZART, with the Cernicke ART, is that we are explicitly, I'm not going into many detail, but I'm just showing you that the single difference between the two equations is the introduction of the deformation theory. So we have done a reconstruction algorithm that is aware of the flexibility. And this has an important the effect is very, very good. Here is a typical data set, and we present zoom when no heterogeneity correction versus heterogeneity correction. The differences by eye are substantial. The differences when you compute local resolution are substantial. And I wish I could go through a number of cases now, but all of them are hot specimen with collaborators, and at this moment they are not yet finished. But really, if you have a case of continuous flexibility that can be modeled by flexibility field, which is not always the case, this is working very nicely. So, and get higher resolution in that blurred areas of the map where you may get stuck, you may not be able to model. So think about this. We understand that we are missing a number of things, and one of them is really this snapshot, the conformational field I'm presenting you, half a million point there. Perfect. How things happen? What is the time? I'm not understanding the time. But there is no time. We have got all the images, and we don't have a time stamp. Who could give us a time stamp? Molecular dynamics. So we are working, and we are not only working, Isabel is also working with Slavica in trying to mix this molecular dynamics information into the reconstruction process. The link is very, I think, it's very obvious and very promising. The limitations, I have started with them saying that we have difficulties in our sample preparation. The air-water interface may interfere in ways that may be very specimen dependent with the conformation that we get. Is therefore difficult to think in energies and thermodynamics and things like that. That we are working with that with a number of people. We are a software producer lab, so we are CPN, that is our main thing, is being interfaced with PRODI, Ibet Bahar molecular dynamics simulation package to really start exploring these things and other things. Let me finish with a point, is that we realize that all these new tools developed by us and developed by others are not the most easy tools, and they are not straightforward. And so what we have developed is within our CPN software, which is a workflow integrator, we have introduced our methods and other methods. CryoDragon is there, everything related with the work that Slavica is doing is there. So, and Gaussian mixture model is to be there very soon. So you can really access a number of ways to analyze your data within the same environment. This has just been published. It's not only that it has been published, because sometimes things are published that may not be so easy to use. No, is that this is work performed in the context of INSTRUCT-ES, in the context of a European infrastructure that has to provide service and access, or the facility that you have here. So the Flexibility Hub is an INSTRUCT service at the moment. You can ask for this when you apply to INSTRUCT. And we have had in June this year, very soon, but just two months ago, but we have had the first course on Flexibility Hub. So you have there 20-something people working in Amazon with this, and if the software is not ready, you are going to have everything, every bomb possible in the way. So the fact that I am putting you this ad, I understand that Madrid is far away from here, but the point is that it is at the level in which we can give a course on that. And in the nutshell, we obtain quantitative information on flexibility landscape. We have a way to, in certain cases, undo deformation. Undo deformation, understand, is a mathematical approach to reduce blurring caused by the incorrect reconstruction process that you have used. Okay, we are not correcting any motion of the macromolecular. Everything has been made easy, within quotation, in the Flexibility Hub of CPN, and we are still working the connection to biophysics that we want to do. We acknowledge is will not be easy. And this has been possible because I'm not alone, and really there are very good people in the lab, especially David Guerrero, fantastic finishing PhD student, one of the most brilliant PhD students I've ever had. James Trigger, UK postdoc, first with Yvette Bajar, so an expert in molecular dynamics, and Carlos Oscar Sanchez Sorzano, who is the other principal investigator in the lab. And with that, I'm done, and I am open to questions. Thank you.
Thank you for the great talk. Now we have some time for the questions. Eric?
Very nice, thank you. I'll start with the end of the talk, I guess, with your ZAP method.
Yes.
So you need a consensus map, but
yes.
You know, what kind of resolution do your algorithm work, and how much flexibility can it deal with?
Very, very good question. Is that, of course, if you have a complete blurring, there is nothing we can do, because really there is no information for many things. So typically we are talking of having something in the 6 angstrom, 5, 6, something like that, and we are able, in many cases, to get to the 3, 4, something like that. In one case, we had a crystal order that was insisting in having 2. Okay, we didn't reach 2, but to have something in the range of 3, 4 from 5, 6 is something that, and this may be the difference from me.
So I have 2 questions. I'll start with the first one. So I've noticed you're starting using UMAP instead of PCA, and it's something that works also quite a lot better with Shanicha, but I don't know why. Do you have any idea why?
Well, I mean, UMAP is another representation, as you know. Sometimes it is better, sometimes it is worse than PCA. Sometimes the UMAP map look like abstract painting. We cannot do much with them, and then we sort to the PCA analysis, because there we understand it's more linear.
And my second question, maybe a little bit provocative, but are we at the stage where maybe we don't need 3D maps anymore, or are we at the stage where maybe be good enough to get prediction of the model using AlphaFold or other prediction tools, and then just collecting 2D data, then matching the two using the model to validate, or the 2D data to validate the model, and then understand if the homogeneity just on the 2D without needing a nice polished 3D.
Well, I think that since we do not have data on this rare conformation and on this flexibility, there is very little room for training any neural network on this flexibility thing. With time, there will be fantastic. And another possibility that one could thought that it doesn't happen to us, but you can imagine, is that AlphaFold evolved more, the complex, the multimer AlphaFold also gets fantastic, and then you don't need to make the ensemble or the average conformation, and you can just start with the AlphaFold multimer thing. However, the flexibility will not be coming from AlphaFold multimer, but it will be coming from the images. You would be saving their marginal thing, that is to make the, because we need still this method at this moment. In practical terms, all these methods require that you make a prior angular assignment to your images. This also answers in part your question. If you don't have anything there, you are not going to do a proper angular assignment. They can do a refinement, but we are all worried in overfitting. We are all worried, are we going to produce or some conformation, or just by changing a little bit the pose, we probably don't know. We have the mathematical capability to do it. Another thing is that we yet are exploring if it makes sense.
So most of these algorithms are the consensus maps. So I was just wondering if you have a lot of particles which have like wrongly assigned orientations to them, how do they affect the algorithms?
Well, is that the first thing we do in our workflows is to make a consensus analysis of angular alignment. So when we process a data set, we do it in the CPM. We normally try to process it with Relion and CryoSpark one or several times. And then we have the tools to tell you how many images are consistent in between runs or between methods. And normally we keep those images that are consistent. We don't keep the images that are different runs of the method or different methods are giving you different orientation because you don't know which one is true, if any. And so we filter them by that. So in principle, we should not have cases in which the particle assigned, the angular assignment or projection geometry assignment is not stable. But you would be surprised how many times. I mean, easily 20%, sometimes 60%.
It's okay, I've got two questions. The first one is with your classical Zernike approach. It looked like you were the differential equation showed you finding the minimum across the absolute values of that vector field. Why were you doing it across the absolute values, not the whole entire vector field? You showed the equation showed that you were looking at that trying to find the minimum across the absolute values.
Let's see. Okay, yes.
Is there a reason for that? Because I guess sometimes you're going to have negative values of deformation.
You're right. I mean, I can give you yes. I mean, I was happy in these two things. One, now with head CNN, we are using L1 instead of L2, but actually we are using in this formula is L1 as well. So maybe this is one of the reasons. L2 is fantastic, the quadratic thing. When you have a large error, it is amplified, but it sometimes is too amplified. And really, you want in very large data set to not amplify so much. So L1 doesn't have the square. This doesn't have the square. And also, as a way, how do we do this in practice? I have been surprised by how did we do it? It was with power optimization. We didn't want to go into gradients and things. But these optimizations are completely now replaced by an encoder-decoder. It's much faster, and the global minima or local minima is probably closer to the global.
So my next question is, our group is very, very interested in obviously uncovering protein dynamics. And what we've found is that if you re-prepare specimens from scratch and then redo the imaging again, so like actual biological repeats of
biological, not technical.
Yes, so not technical, biological repeats. We have observed that different flexibility landscapes. So I guess this is a question in two parts. The first is, have you made any attempts to compare variability between specimens? And the second is, are you worried about the overinterpretation of an N1 experiment in terms of the protein dynamics, the folding landscapes, and all that sort of stuff?
Completely. I mean, I mean, is that the whole field should be aware that one experiment may have many variables that you do not control or that you do not know that even you should control. for instance, with all the thing of the spike, something probably obvious that we didn't think, temperature. We have much more flexibility when you were holding the tube at 36 than when it was at 4. Probably it was obvious, but we didn't think about that for some months. So, and we were getting different answer, and I mean, the purification has had problem, and there was no problem at all, is that we were not properly stating the condition in which we were making the analysis. And you are completely correct that many times we work with, we go to microscope, we take images, and we take one set of images with one specimen. It's not enough. Clear.
Yeah, we're finding this too. It's not enough. We need more microscopes now.
Yes.
So, or better samples, right?
No, better sample. The problem is not that is that you are studying the system. So a complete reproducibility in the system is something that you may not have yet achieved. Eventually, when you study this enough, you may achieve a complete reproducibility. But, excuse me.
James Barrett from the University of Oregon. Question for you on your CNB polynomials.
Yes.
How many parameters are you solving for, and what's
Perfect. Perfect. The parameters, which are the parameters? The parameters are the number of the number of terms of the basis that we are using, and normally we are in between 20 and 40, something like that. In principle, we could have larger, but 20 and 40 is something that give us a smooth landscape, and we think we are not overfitting. Is that.
What's the computation time?
Well, the computation time of the Cerniques was huge in CPUs, and once we got everything in GPUs, it's a matter of hours. And the same for the south, that you would have to have into account that you know probably that ART, arithmetic conformational technique, is considered a slow approach. It was very convenient because conceptually it was very simple in the forward mode. We put but however, when we have properly this is a collaboration, a very fruitful collaboration with the Czech Republic, with Masaryk University. Everything that they do, that we do together in GPUs, is then doing the GPU stuff, and they may change we may change the algorithm together to really get it better into the memory and whatever. So it's not a simple. We could do a simple thing, but not what they do. So at this moment, there are no concerns of if you have GPUs, there are no concerns of time. Before it was days or even weeks. Okay.
I would like to ask the last question. So, is there any limitation on the size of the molecule and thickness of this kind of flexibility?
I mean, we have been using that for HER2, and HER2 probably is in the low side. HER2, the extra domain part, we are talking about 80K. We would be more comfortable with larger things, but we have used for that one. So this is a low limit that we have there.
Thank you. Yes.
Another question about symmetric particle.
Yes.
So are those methods problematic when it comes to symmetry, because we are being misalignment and variability?
Yeah, we are completely correct, and we haven't done much about that. Not that we haven't done much about that, is that none of the cases we are working with at the moment have any symmetry. So we are, but I mean, I can imagine that there are cases in which there is a symmetry and we should take that into account properly. We haven't done it. It would be for doing in the course of the collaboration.
Okay, thank you everyone for joining us today for this seminar, and I would also like to thank our speaker who gave a really interesting talk. Please join us in the atrium for some refreshment. Thank you.
Thank you.